the number of particles. Here's what we know so far. We know that according to Boyle's law, pressure and volume are, hang on, let's give it a minute to catch up and I'll edit that out. There it comes. If pressure and volume are inversely related, we can see Boyle's law, P times V. We introduced the next variable, the temperature, and we decided that temperature belongs on the bottom of our ratio, volume over temperature, Charles' law. P over temperature is Gay-Lussac's law. Temperature is directly related to the P and the V. We have a next variable to consider, and that's N, the number of particles. When I consider where N belongs in our relationship, I place it on the bottom. N, the number of particles, has a direct relationship to the pressure of the container. And that just makes sense. If I have more particles in a container, we have more collisions and the number of pressure units would increase. Same is true for volume. Think of just blowing up a balloon. If you start increasing number of particles as you blow up a balloon, the volume gets larger. The number of particles has a direct ratio to the pressure and the volume. So that fourth variable, N, where N stands for the number of particles, belongs on the bottom of our relationship, PV over Tn. We set that equal to a proportionality constant called R. R is known as the ideal gas constant. And we understand that in math talk, when we have a constant in math, it's a number that does not change. PV over Tn set equal to R is the ideal gas law that says pressure and volume are inversely related. P's and T's, V's and T's have that direct relationship, and we've introduced our last variable N, the number of moles. Now it's not a PV-MERT problem, it's a PV-NERT problem where N just happens to represent mole values. When we count in chemistry, we count by mole units. We don't count individual particles. So PV over Tn, where N stands for the number of particles, counting with a unit we're familiar with called mole. Now, if we think about standard conditions and what Avogadro's hypothesis once taught us, back in the old days when we first learned about the mole map, it's covered back here, but if we were in the center of the mole and we want to head north to the balloon, there was a standard volume unit we used. It was 22.4 liters. We know that 1 mole of any gas at standard conditions is 22.4 liters big. If we were to take those standard values for P, V, T, and N, we can solve for the gas constant called R, the in the PV-NERT problem. We do that 3 different times because we know we have 3 different values for standard pressure. We have a metric system standard value called a kilopascal. We have a familiar system here in America. We use atmospheres. And, especially in our laboratory, most barometers have a meter stick next to them, and we measure a column of mercury in terms of millimeters of mercury, the height of a mercury column. So we're going to one at a time plug in standard values and solve for R. Once we know the R constant, we can PV-NERT any equation and know the value for R to plunk in. So we'll do that first using a kilopascal of pressure. Standard pressure in a kilopascal, I'm just going to get my parentheses ready for standard values and we'll solve for R. Standard pressure in a kilopascal is 101.3 kPa units. Standard volume, 22.4 liters. Standard temperature, 273 Kelvin. And the standard number of particles being 1 mole. So those terms STP, that's just Avogadro saying that 1 mole of any gas at standard temperature and standard pressure has a volume of 22.4 liters big. So plunking in PV over Tn using ideal conditions, we get a gas constant. If we hit standard pressure, 101.3, times 22.4, the standard volume, divided by the Kelvin unit of standard temperature, 273, we get a gas constant, 8.31. R, when we PV-NERT, 8.31, if the pressure is in a kilopascal. So if I'm reading through a PUV-NRT story problem and the pressure is given to me in a kPa, whatever that pressure might be, if the unit is in a kilopascal, the R constant I'll place in is 8.31. Now that's the most common system everywhere else but America. It's called the metric system. So most common unit you might see other places, the kilopascal. We also have a system called atmospheres. We understand that an atmosphere has a standard value of 1. 1 atm, or 1 atmosphere of pressure, is the standard value. When the balloon is 22.4 liters big, containing 1 mole at 273 Kelvin units. If the pressure is being measured in an atmosphere, we'll have a different R constant, simply because we had a different number placed in for the value of pressure. Solving for R in atmospheres in ideal conditions, 1 times 22.4 divided by 273 times 1, and we get a gas constant, 0.0821. And I'm going to place that in. If I'm working a PUV-NRT problem and the R constant is given to me as an atmosphere, I'm just simply matching atmospheres go to the R constant 0.0821. And I made mention the most common unit for pressure in our lab is called a millimeter of mercury. It's just the height of the column, just like a thermometer. And that's 760 millimeters of mercury high at standard conditions. I'm going to solve one more time for the R constant using Avogadro's hypothesis. 1 mole of any gas at STP is 22.4 liters big. And once we know those R constants, we only have to solve for them once. They're constants. Once we know them, we plug them into the of a PUV-NRT problem. So we'll hit 760 times the molar volume of 22.4 divided by standard temperature of 273, and I find 62.4, I'll say. If we're working a PUV-NRT problem and pressure is given to us in a millimeter of mercury, I have to match the R constant to the 62.4. In order for these units to work out, we've made the pressure units match the R constant. So introducing the last variable, we have P times V set over to N times T equal to this constant we called R. In a more familiar format, we simply rearrange those variables. PV over NT equal to R, we simply rearrange. P times V is equal to nRT. You can see that more familiar format of the PUV-NRT equation called the ideal gas law. Pressure times volume set equal to the number of moles times the ideal gas constant times our temperature. Now, a couple of things before we turn the page and actually try an example. Let's make some important notes. Pressure and the R must match. So whatever the pressure unit is, be sure that you're placing in the appropriate R constant. There's another thing we've done, and that was to volume. Every time we solve for the R constant, we put in a liter unit. So there's no choice now in this algebra. Volume must be in a liter, or the R constant won't match. Now in the last set of algebra, it absolutely didn't matter what they were, just so they were the same on both sides. But when we PUV-NRT, we've got to have a liter unit to have the R constant work out. Of course, temperature must be in a Kelvin, always, always, no Celsius allowed. And N stands for moles. N is a mole unit, the way that we count particles in chemistry. So we have pressure determining the R, volume in a liter, the N is a counting unit known as the mole, and T is the Kelvin temperature. We have what we need to try our first PUV-NRT problem. Why don't we flip over and find that on the top of the next page. Now as we read PUV-NRT problems, I just like to get my parentheses ready so when I see a number, I can place it into the appropriate spot in my PUV-NRT equation. It's just a strategy that I like using. If PUV equals NRT, PV equal nRT, I can just find numbers and place them in the appropriate parenthesis, and I have what I need to punch that missing number. The algebra will be friendly. We'll have 5 variables. One will be missing, and we'll just pull out the missing variable. So I'll read and just ask you to follow along with example 1. It says we have a rigid steel container, the volume of 20 liters. Now that's in a liter unit, so I'm all set, no adjustments necessary. I'll just put that in as 20 liters. It's filled with nitrogen gas, and the final pressure is 20,000 kilopascals. 20,000, that's a high number, 20,000 kilopascals. Now, before I go on, this kPa unit, well, that just determined my R constant. So not only do I know P, I also know R in the PUV-NRT. So as we get more familiar with working towards memorizing, although they're on a knowledge poster, I have to remember to match my R constant to the kilopascal pressure. So I can see kPa, the R constant is going to be our 8.31. So now I know to plunk in 8.31, the value of R that we calculated from that previous page. So we have 20,000 pressure. kPa unit told me to use 8.31. Volume was 20 liters. Temperature was 28 Celsius, which is 301 Kelvin units. We'd like to know N, the number of moles. Ready? So the algebra is just start on the side without the variable PV divided by the product of RT. So I'm going to hit out for us. Please hit with me. Solving for N, where N will be moles of nitrogen. I know it's not a PUV-NRT problem. N stands for numbers of moles, the counting unit of chemists. So we have 20,000. That's a big number. Times 20 liters. We'll divide by the gas constant, 8.31, and 3.01, the Kelvin temperature. We could also, if you prefer, doesn't matter, we could use parentheses and find the same answer. You could put a parenthesis in either direction, we'll find it. You can divide by twice, or you can find that you have a product inside the parenthesis. I have 159.9 moles of nitrogen. I think I'll just round a little bit. I'm going to call that 160 moles of nitrogen. 159.9, I'll just round it in. So when we first PUV-NRT, we found the number of moles, the counting unit of a chemist. Inside of that mole unit are actually some other variables. We could do a little mole map work and solve for grams. So interesting, if N stands for the number of moles, hidden in there are some other things. Moles we know to be equivalent to saying grams over molar mass. Just an old mole map problem. If I'm in the center of the mole and I want to know how something weighs, going out to the scale, we know to use the formula weight or the term molar mass. So hidden in the N, the number of moles, we have grams and we have molar mass variables. So if I want to convert my moles of nitrogen into a gram of nitrogen, we're going to do a little mole map work. Using the molar mass of molecular nitrogen, we can easily convert a mole number into a mass number. Moles times formula weight, so just while that same number is on my screen, I'll go times 28, and we've converted into a gram. And that's a big number, but that makes sense. Look at the high pressure. It's got to be a lot of particles giving 20,000 kPas. 4,477.7 grams of nitrogen gas are held in that container. Now notice I have the identity of the gas. It was called nitrogen, so I can place the label with that unit as well. 4,447.7 grams of nitrogen held in that container. Talk through the strategy. We put nRT first, finding N. N allowed us to convert into grams. N, that target variable, has other variables inside of it. Grams over formula weight. Let's go on and read a second example for a PUV-NRT equation. This time we're in a deep underground cavern. And that cavern contains 2.24 times 10 to the 6th liters of methane gas. It's natural gas at a pressure of 1.5 times 10 cubed kilopascals. Temperature 42 degrees Celsius. We're being asked to solve for grams. Now I don't hear a G in a PUV-NRT problem. There is no G, but hidden inside one of the other variables is a G. I have to pull out moles, and from moles I can do some mole map work. So when I'm being asked to solve for grams, that's my clue that it's a two-step problem. Step 1, we got to find moles. And then step 2, we got to convert moles into grams. That's mole map work. So we did it two separate problems up above, but sometimes we're going to see it directly right in the same problem. If grams is our target variable, we pull out moles first. So N in the PUV-NRT problem, I like to get my parentheses ready. It's just something I've always done. PV equal nRT. And that way I can just plunk numbers in as we trip over them in the story problem. The volume of our cavern, quite large, 2.24 times 10 to the 6th liter units, already in a liter, so I don't have to adjust that volume. The pressure, 1.5 times 10 cubed kPas, kilopascals. And while I have the kPa unit, that also tells me the value for R. It happens to be the same as up above. A kilopascal, I have to match that R constant to that 8.31 value. Temperature within this cave is 42 Celsius, so before I can put that into the temperature, we convert it to a Kelvin, 315 Kelvin units. We know pressure, volume, the gas constant R, and the Kelvin temperature. We're going to be able to solve for N, which are moles of methane. PV divided by R and T will pull out N. A little algebra for the missing variable. Hit with me. With 1.5 times 10 to the 3rd kPas times 2.24 times 10 to the 6th liters divided by the product of the gas constant, 8.31, and 315 Kelvin units. The moles of methane. That makes sense to me actually, because this is a large cavern. We have 1 million moles. 1,283,594 moles of methane gas. I wouldn't light a match down in that cavern. A whole lot of natural gas down there. Well, we have moles, but it actually asks for grams, so we're not quite there. We have step 1 accomplished, though. We pulled out N in the PUV-NRT problem, the number of moles, just a little mole map work, and we've got it converted to grams. Now, methane is CH4, so I'm just going to use its formula weight. 16 grams, the molar mass for every 1 mole. And we can cancel that mole unit out and convert to grams. So while this is on my screen, I'm going to make it even a larger number, multiply by its molar mass. We end up with 20,537,505 grams of natural gas, CH4. In our first example, we were asked to solve for moles first and then mass, and now they've just combined it into one story problem. It's the same strategy. If we're trying to find grams of a compound, that's a hidden variable inside the number of moles. Let's read a next problem looking at some helium gas. We have a temperature and it's a rigid hollow sphere, and again these are saying rigid underground caverns or fixed volumes. The volume isn't allowed to change, so every one of our PUV-NRT problems is going to have a volume that remains fixed. I like to just get my PUV-NRT parentheses ready so I can see where to place numbers as I read about them. So that's just a strategy I've always done. First number, as we read about our story problem, the temperature is containing, here it is, 685 liters, and that volume unit does not need adjusting, already in a liter unit, so I'll just plunk it in the V parenthesis. Temperature is given to us in a Kelvin, 621 Kelvin unit, so no need to adjust there. Pressure is in a kPa, so I place that in the pressure variable, 1.89 times 10 cubed. And again, a third example, they're not all kPa's, but this is the third time we're seeing 8.31. Just matching the gas constant to the pressure unit. It's asking us to solve for N, the number of moles, and I don't need to do any mole map work, it's just asking for moles, so that indeed does match what N stands for. When we find N, we'll have moles of helium. Starting on the side without the variable, we PV divide by nRT. So let's hit together. 1.89 e to the third power times that volume of 685 units. We'll divide by the product of 8.31 and 621. I found 250. I'll just round into a 9, 250.9 moles of helium. So I don't have a next step. It only asked me to go as far as moles. Moles is the N variable, the number of moles in the PUV-NRT problem. Now the first three examples, we targeted the same variable, N, each and every time. But I don't think they're all like that. You can have any of the variables be asked for. In number 4, we have an interesting question where it's asking for a pressure and it doesn't give us a target unit. If we're being asked to solve for pressure, let's go ahead and get our PUV-NRT parentheses ready. That way, every time we see a number, we're able to just plop it in. If pressure is being asked for, I'm just going to place that in as my pressure, my target variable. We know that that will be equal to PV equal nRT, and we'll place those in as we find them. The number of moles, 0.45. The temperature of 25 Celsius is 298 Kelvin. The volume is given as 0.65 liters. And those are the values we have. We have N, we have T, and we have V. We're being asked to solve for pressure. We have a decision to make, and there's absolutely 3 correct choices. If I put 8.31 in for the R constant, pressure will be a kPa. Another lovely choice, we could put 0821 in and have an atmosphere. 62.4 will tell us to write mmHgs. Since it didn't tell us what pressure unit, we just get to select. So this one has like 3 possible correct answers. Let's mix it up a little bit just so we don't end up with the same answer. I'm going to say 0.0821. I'm just picking a different R constant just so we can see it come out differently. And as soon as I wrote 0821, I now know to report my pressure in an atmosphere. If I had placed 8.31, I'd write kPa. 62.4, and I'd write mmHgs. It doesn't matter. We just need to select. Since I mixed it up a little bit with a different R constant, we're going to solve for pressure. Remember to start on the side without the variable. So nRT divide by V. The number of moles was 0.45. Times the gas constant, 0821, times that Kelvin temperature of 298, divide by the volume of 0.65 liters. I found 16.9 atmospheres. We could have found 3 different answers just depending upon the R constant. The R constant of 0821 determined the atmospheres of pressure. nRT divided by V gave us 16.9 ATMs for atmospheres pressure. We'll continue on with a sample of a child's lung capacity. It says what child has a lung capacity of 2.2 liters. How many grams of air do her lungs hold? Assume a pressure of 102 kilopascals, very close to standard pressure. Normal body temperature is 37 Celsius. We want to know how many grams of air, so let's get our PUVNRT parentheses ready. I know that step 1, I have to get N out. N is going to represent moles of air. And then I can figure out from there a little mole map work to find grams. So N is going to be my target. I want to know how many moles of air so I can use the formula weight and convert it out to a gram. So N is my target. Hidden in the N variable, the number of moles, I can find grams by doing mole map work. Capacity of the lung, 2.2 liters. The pressure unit, 102 kPas for kilopascal, determines the R constant that we match it to be, 8.31. Body temperature is 37 Celsius. In a Kelvin unit, the body temperature is 310 units. We have PV divided by RT, and we'll find moles of the air inside of this child's lung. Let me move that up. Alrighty, so 102 times 2.2 divide by R divide by T. And I'm finding 0.087 0.087 moles of air times its formula weight. And air is a mixture, but we're going to assume 80% of air is nitrogen gas, so it's fair to assume 28 grams per mole. So while I have my mole value on the screen, I'm just going to use the molar mass they're giving us for the air as 28. And that child's lung capacity, 2.44 grams of air being held in her lungs. So we PUVNRT for the N variable. N stands for number of moles. As we find moles, we can use formula weight to convert out to a gram. Friends, we have one more, and that will finish the PUVNRT examples. Let me read through number 6. Just thank you for your patience as you're getting wiggly, I know. We're going to PUVNRT one more time to finish this example set. I'm going to get my PUVNRT parentheses ready. The previous problem leaked down in this area, but that goes up above. Alrighty. So, what volume, I now know my target, I'm looking for V, will 12 grams of oxygen, I don't hear a G in a PUVNRT problem anywhere, so I'm just recording that down below. It doesn't have a parenthesis. There is no G in a PUVNRT, so I'm recording it below the parentheses. Temperature is given as 25 Celsius. I have to convert into a Kelvin, so I can put 298 K in there. The pressure, 52.7 kilopascals. That pressure unit of kPa tells me to match with the gas constant, 8.31. N stands for the number of moles, which I can easily determine with a little mole map work. Given the mass of oxygen, we can convert to moles of oxygen, and that becomes the N in our PUVNRT equation. So a little mole map sidetrack. where I take the mass and I divide by the molar mass of 32, and that 0.375 becomes the number of moles I can PUV NRT with. N stands for moles, so I can easily convert grams into moles with a mole map problem. Let's hit for the volume. So I've got my moles in there, nRT, 0.375 times 8.31, and the temperature 298. We'll divide by 52.7. In the volume we find 17.6, and the unit must be a liter, and the label is oxygen. We've gone through many examples PUV NRTing. You have what you need to, if you haven't yet, grab your worksheet off of the bench up front. It's a one-sider, trying to find you a silver lining there. 10 examples of a PUV NRT problem. Yeah, try to grab one for everybody. Thank you for being a good audience as we recorded.